Try that again. All right, so like I said, we're not going to get very far today on these notes. We will just, listen up. Okay, so the furthest we're going to get today is probably to Roman numeral 3, letter C, which is, not very far down the paper, okay? So we're going to take our time here, right? We're going to ease our way back in, and I've got one worksheet for you guys to work on that we'll probably be able to do most of it in class, I'm guessing. If we get most of it done in class, then we will probably have a quiz on Monday. It will not be, listen up, we will probably have a quiz Monday. It will not be first thing because we'll take some time to review since, this is our first day back. And I'm not entirely sure we're going to be here Monday. So we'll see what happens, all right? But yeah, just know that we'll probably have a quiz at some point during the day the next time we have class. I said class really weird just then. Class. It's like the word got stuck or something. All right. Anyway, what we're going to talk about today is nomenclature, okay? Anybody know what nomenclature means that I didn't just tell you the answer? Yes. Okay, sounds familiar. Yep. Does sound familiar. Nomenclature. What does nomen maybe sound like? Okay. I don't know where I thought I was going to get with that particular question. It sounds like, yeah, there you go. Thank you. All right. You're tracking with me here. All right. Kind of sounds like a name, right? Okay, so naming. Sure. Nomen sounds like naming, right? Yeah, that's what it sounds like. Come on. All right. So when we talk about this, we're talking about naming compounds. Now, before we get into the naming part, we need to talk a little bit about how these compounds form. And so now I'm going to need you to think back to 8th grade a little bit. And I know we've established that some of you, it's all a blur. But we need to talk about some of the things that you did talk about in 8th grade. Okay? So there's a couple of different types of chemical bonds, or forms of chemical bonds. I don't know why Yoda's there, but I like it. So there are two types of bonds. Do you remember what those two types of bonds are? Ionic and covalent. You remember talking about those? Okay? So you can have an ionic bond or a covalent bond. Now, let's see if you remember this. Ionic bond happens when? Or what do the electrons do in an ionic bond? Very good. Okay. Now you might have gotten that from the notes, but okay. It's a transfer of electrons, right? So in an ionic bond, the electrons are being transferred from one atom to another. One of them is losing electrons, the other one is gaining. Okay? That's an ionic compound. Now, with covalent, what's the difference? They share electrons. Okay? So some valence electrons are shared between atoms in a covalent bond. Okay? So those are the two major types of chemical bonds that we're going to talk about in this class. There is another type called metallic bonding that we're not going to talk about a whole lot in here. We will mention it at some point. But these are the two major types, ionic and covalent. All right? I don't know what that click did, but do you have a blank to fill in on that one? Nope, okay. But just know this. These are really the extremes, okay? Ionic and covalent are kind of extreme opposite ends of the spectrum. Okay? So most things fall somewhere in between those two. Okay. So when we're naming these chemicals, it depends on, the way that we name it depends on whether it's ionic or covalent, okay? A lot of these things have common names. You might be more familiar with the common names of some of these things than you are with the actual official names. Okay? So some chemicals that are always named by their common names. Water, right? So water is not typically called dihydrogen monoxide. Okay? That would be its technical, scientific, chemical name. Now this is actually kind of funny. There were a couple of guys who just thought they would have some fun with this a few years ago. They went around and started a petition. And they were getting people to sign this petition. The petition was to ban the use of dihydrogen monoxide. Okay? Nobody knows what dihydrogen monoxide is, right? Nobody knows that that's water. So all these people were signing this petition. You know, they're like, oh man, yeah, we got to get the dihydrogen monoxide out of here, right? That stuff is killing people. And so, you know, they were giving them statistics like, you know, dihydrogen monoxide kills more people every year than, you know, and then they would name some other things, which is true. I mean, water does kill people sometimes, right? You know, from drowning and, you know, things like that. Maybe if you count, I don't know, other various things that could happen with water. I don't know. But point is, you know, they were giving out statistics like, yeah, dihydrogen monoxide is found in 100% of cancer patients. 100% of them have dihydrogen monoxide found in their system. You know, and these people are like, oh, this is horrible. We have to sign this petition. You know, they got millions, literally millions of people to sign this petition to ban water because they were calling it dihydrogen monoxide. So anyway, now you know, so you won't be taken in by that sort of petition if that sort of thing ever happens again. NH3 is always called ammonia, not nitrogen trihydride. Ammonia is another fairly common one. Have we talked about ammonia this year? I think we did when we did the gas tube thing back there. You guys remember that? Ammonia was one of the things that I put on one of the cotton balls. Do you remember that's what they put under people's noses to revive them when they passed out in the 1800s? And they realized that's not very good for you to be breathing in. Yeah, ammonia does not give you pneumonia, but yeah, it does sound similar. Okay, so, okay, now we're already on Roman numeral 3, so we've just got a couple other things to do, and then we'll do some practice, all right? Some compounds formed from ions. So now we're gonna talk about ionic bonding for just a second, okay? We're gonna forget about covalent bonding basically for the rest of this unit. We'll take a test just on ionic bonding, and then we'll come back and talk about covalent bonding, okay? So that's really what we're focusing on right now. If you get a cation plus an anion, it makes a compound that's called an ionic bond. Now, we talked about cations and anions, didn't we? Okay, which one is positive? The cation is positive, remember? Okay, and the anion's the other one. That's the one that's negative. Okay, so an example of that, if you've got sodium, which forms a 1 plus ion, and chlorine, which forms a 1 minus, then you end up with NaCl. Anybody know what the name for NaCl is? It is salt. What's the official technical name? Close. Not sodium salt. That sounds like you should, you know, patent that brand name. I feel like you'd make money off of that. Sodium salt. Sodium salt. Just fun to say. Sodium chloride. You guys have heard it called that before, right? Sodium chloride. That's the official technical name for it. Okay. Okay. For an ionic compound to be neutral, it requires an equal number of positive and negative charges. Okay. So if you notice here, sodium chloride is a neutral compound. It does not shock you when you touch it, right? Anybody ever been shocked by salt before? Probably not, okay? So it's neutral, right? It doesn't have a charge when you touch it. The reason for that is the sodium has a 1 plus charge, the chlorine has a 1 minus. One of each of those go together, and you end up with just NaCl. The positive and the negative cancel out, and now you have a neutral compound, okay? So to have a neutral compound, you've got to have those equal numbers of charges. In other words, when you add the charges up, they have to equal 0. All right, now, this is what you need your periodic table for, okay? You need to know the typical charges in these groups. Now, remember how we learned at the very end of the semester that things that are in the same column on the periodic table will have the same properties? Remember that? Okay? So we remembered, or we learned that oxygen and sulfur will typically have the same properties. Nitrogen and phosphorus will have the same properties. The noble gases will have the same properties. What's going on here? Oh, no, that's right. Except for, I don't know why that is there. H minus. What happened?
Oh, no, they put it H on both sides because of the negative.
Huh, okay. Yeah, I guess I can see that. You're not going to have a hydrogen right here, okay? So just kind of disregard that, okay? Normally in this class, hydrogen, now it can have a negative charge if it pairs with certain things, but normally it's going to be a positive, so we'll, for the most part, we'll keep it over here, okay? But you need to know that everything in this column, this far right column over here, the noble gases, they're going to form a charge of 0. In other words, they don't form a charge, okay? What that means is these atoms in this column right here, the far right column, you remember what they're called? Those are the noble gases, right? Okay, the noble gases do not give away or gain electrons. Okay, they're happy the way that they are. They don't have to give away or gain electrons. Okay, so they're going to have a charge of 0. So above that column, you probably want to label 0. All right. Now, everything in the 7th column, and is there anywhere in here that we talk about valence electrons? Because we should, yeah, we should talk about that. Okay, you guys remember from 8th grade talking about valence electrons? No. Okay, valence electrons are the ones on the outside. So you remember the Bohr model of the atom that we drew last semester. You've got your nucleus in the middle, you've got your electrons on the outside, right? So let's say that we've got a couple electrons out here. Those are your valence electrons. The ones that are in these inside rings, those are just called the inner or the core electrons. Okay? The valence electrons are the ones on the outside. Somewhere on your page, you might want to just draw a picture of the Bohr model, put a couple electrons on the outside here, and label them as, these are valence electrons. Okay? That is an excellent question. Okay, the question for the video is, if the electrons, or if opposites attract, why don't the electrons basically just spiral into the nucleus? Okay. That's the problem with this model of the atom. That's why this model of the atom really doesn't work. Okay? So basically, it's kind of like with, I guess you could sort of think of it like gravity a little bit. Like planets orbiting around the sun, what keeps them from spiraling into the sun? It's the fact that they already have some energy. They're constantly trying to escape in one direction, right? So a planet is trying to escape in this direction, but it's being pulled in this direction by whatever's in the center. So then your net movement ends up being kind of in a circle. Does that make sense? Yeah. Now, the problem here is there is some friction and resistance and all of that that means that this thing should lose energy over time and eventually spiral into the nucleus. And that's when you need quantum mechanics, because this model of the atom doesn't perfectly explain what's going on here. So that's an excellent question, and that's one that scientists actually asked that led them to disprove Rutherford's model of the atom. Okay? No, that's all right. That was a really good question. I'm just trying to find my flow of thought here again. So we were talking about the last column here, and we were talking about valence electrons. Okay? So there's a really handy way to figure out how many valence electrons are in an atom. Let me erase some of this stuff because it's getting messy. All you have to do is look at the group number at the top. Okay? Now, we're going to forget about these for a little while. These get a little bit tricky, the ones that are in the middle, the transition metals. Okay? What else do we call those besides transition metals? Can you remember? Well, no, the metalloids are over, they're the green ones right here, right? They're the ones on the stair-step line. Well, these are metals, yeah, but I'm talking about the ones in the middle there, okay? D block, very good. These are the D block elements because these are the ones where their last electrons are going into the D orbitals, right? Okay? So we're going to just kind of ignore the D block and the F block elements for right now when we're talking about this. We're just going to talk about the S and the P block. But if you look at this number right here, that tells you the number of valence electrons that these atoms have, okay? So in this column, this first column right here, everything in that column has 1 valence electron, okay? Everything in the second column has 2 valence electrons. Then we skip the middle, okay? Everything in this column with aluminum has 3 valence electrons. That's why sometimes this is called 3A. Now, I think on your periodic table you have it labeled as 13, right? Okay? All you have to do is just, pretend the 1 isn't there, and it will tell you the number of valence electrons, okay? So you've got 3 valence electrons here, 4 here, 5 here, 6 here, 7, and 8. Turns out with valence electrons, the magic number is 8. Okay, every atom wants 8 valence electrons if it can get them. Okay, because what that means is if you have 8 valence electrons, then you have completely full s and p orbitals, right? So you've got your s orbitals here, you've got your p orbitals. And remember, we talked about this at the very end of the semester. That's a pretty stable configuration, right? If everything's full, that atom is fairly stable. And that's why the noble gases they don't form a charge, because they don't want to lose an electron or gain one. They're happy just the way that they are, okay? So then, with this 7th row right here, the 7th column, or number 17, if you've got it labeled there, these are basically, if you look at their electron configurations, they're going to look like this. Now, what do you think those atoms want? So this is, we're talking about, this is the group 7A, or 17 atoms right here. Okay, all of them basically look like this. So what would they want in order to be stable? One more. They're just missing one electron right here, right? So they just want to gain one more electron. If they do that, then they will have a 1 minus charge. Because remember, electrons are negative, right? So if they take one extra electron from somewhere else so that they can look like this, then they have a 1 minus charge. Does that make sense? Okay? Everything basically wants to be like the noble gases. All right? So this fluorine right here, okay, fluorine's not happy because it has, you know, it wants so badly to be like neon. Okay? But it's not quite like neon. So it goes and steals an electron from somewhere, and then it comes over to neon. It's like, what's up, neon? I got 10 electrons too now. And neon's not impressed. Yeah, that's what happens in the chemical world. This is how I imagine this happening, okay? But everything in that 7th column right there, they want to be like the noble gas that's right next to them. So they will go and steal an electron from some other atom so that they can be like that noble gas, all right? So, and they're just kind of pretending, because neon looks at the fluorine and the neon's like, yeah, right, you've only got 9 protons. You're not like me at all, okay? So, you know, neon's not fooled, but fluorine's trying to pretend like it's neon, okay? That's what happens. It's really kind of like, it's exactly like high school, really, if you think about it. I don't know how, but, you know. Anyway, moving on. So, right here you've got 6 valence electrons in this column, right? Okay, group 16 has 6 valence electrons. They want 8, so they need 2 more. Does that make sense? Their electron configuration is going to look like, or their orbital diagram, I suppose, is going to look like this. 2, 3, like that. So they're missing 2 electrons here, okay? So if they can grab 2 electrons from somebody, form a 2 minus charge, then they're going to be like a noble gas, okay? And that's what everyone kind of wants, is those 8 valence electrons. So you just kind of have to think about that, all right? With the 5A, they're going to need to grab 3 electrons in order to be like a noble gas, because they need 3 more. Is that making sense? Okay? Now, here's where it gets a little tricky. You come over to the other side, or the 4A, for example. Now, notice we didn't write any charges for anything in the 4th group. Why not? What do you think? Well, now you have to gain 4 electrons. That's probably not very easy, okay? Does that make sense? So most of the things in this column don't gain or lose electrons. They don't form ionic compounds. They typically share. So we'll just hold off on talking about those until later, okay? But then you come over here. Now here's where it gets a little different. Because aluminum, for example, has 3 valence electrons, okay? It's in group 3A or group 13. It has 3 valence electrons. Now, it could gain 5 electrons to become like a noble gas, but that's really difficult, right? But what's the other thing that aluminum could do? What if it lost 3 electrons? Okay, so if you look up at aluminum, it's number 13, right? Okay? So it's actually closer to neon than it is to argon, right? If it loses 3 electrons and has 10, now it's like neon. Does that make sense? So it's going to be easier for aluminum to lose 3 electrons and form a 3 plus charge, because remember, electrons are like your negative friend. If they go away, you become more positive. All right, so these 3 electrons are going away, so now the aluminum has a 3 plus charge. It's now a cation. Okay? Same thing with 2A and 1A. The things in group 2A, they're going to lose 2 electrons because they have 2 valence electrons. They can just lose those 2 and become like the noble gas before them, and then they'll have a 2 plus charge. Okay? And then everything in group 1 will form a 1 plus charge. Now, what do you think are the most reactive elements on the periodic table? Let's take a shot at it. Which ones do you think are maybe so close to being a noble gas that they can just taste it, and they'll do anything they can to become a noble gas? Yeah, the ones right next to it, right? These right here. Fluorine is the most reactive element on the periodic table. You guys ever heard of hydrofluoric acid? Okay, that's actually not that strong of an acid in terms of the way we usually define acids. The reason that hydrofluoric acid will even eat through glass or other things, if you've watched certain TV shows, the reason that it will eat through things is because the fluorine is so highly reactive. Okay, it will just basically start stealing electrons from anything that it can get its hands on because it wants to be like a noble gas. Now the other group that's really reactive, we're going to have to do a demo probably Monday. This is a fun one. These right here in the first column, the alkali metals, okay? These are just one away from being a noble gas also, right? They have to lose an electron to become like a noble gas. So on the far ends of the periodic table here, the 7A elements and the 1A elements, those are the most reactive out of all of them because those are the ones that are so close to becoming a noble gas. All they have to do is gain or lose 1 electron, okay? These over here are so reactive, you put them into water and they start stealing, or they start giving away their electrons to water, okay? So we're going to do a demo probably on Monday or Tuesday with that, where I'll just put some alkali metals into water and we'll watch them do what they do. It's pretty interesting because you don't usually see things react with water when you put them into water, but those do. Okay? Does that kind of make sense? I'm sorry, that's not on the notes. It should be, but it's on. You have it on the video now, so you can go back and kind of listen to that if you need a further explanation again on the valence electron thing. But that's how you kind of determine those charges. Okay, for now, you have the charges labeled above the columns, so that's going to help you figure out what charge these things are going to form. Okay? You should probably put a 3 plus. Well, you know what? Maybe you should just label aluminum as a 3 plus because that's really the only one in that column that's going to do that. Okay? So we won't label the whole column as 3 plus for the 3A, but aluminum, you should probably label that one as it will form a 3 plus. Okay? Everybody okay with the charges and how that kind of works? Okay. We're going to stop there. Oh, no, one more thing, sorry. Just the, where are we here? No, that's not what I wanted. Did we already write down the, oh, it's down here. Okay, I'm sorry. I didn't realize it was below the periodic table. Okay, so your blank here for letter C, metals usually form cations. Okay? In other words, metals are going to give away their electrons. Now, looking at where the metals are on the periodic table, does that kind of make sense? They're on the left side over here, right? So all of these things, if you look at those, they all have pluses, right? These are all forming cations. Okay? The nonmetals, for number 2 on C, usually form anions. Okay? The nonmetals are the ones over here, and those are the ones with all the minus charges. Okay, so that's it. We're going to do a worksheet practicing how to do this. Oh, you know what? Sorry. One more thing that I should show you on the video. I'll give you this worksheet before we do this, but this should be on the video as well. That way you'll have some sort of reference as far as how this is supposed to work. Here, I'll just hand yours back with this row. Let me pull this up on my green here. Okay. This is really, really easy. All a Lewis dot structure is you're basically drawing dots that represent the number of valence electrons around an atom. Okay? So here's how this works. So for the first one here, it says draw a Lewis dot structure for each of the following atoms. First one is aluminum. Okay? So the first thing you do on any of these dot structures is you just draw the symbol for the element. Okay? Symbol for aluminum is Al. Here's the tricky part. How many valence electrons does aluminum have? Okay, maybe it's not that tricky. So it has 3 valence electrons. Everybody okay with where that number came from? Okay? You just look at the group that it is on the periodic table. It's group 3A or group 13, so that's got 3 valence electrons. Then all you do is you just draw dots around the structure. There's probably technically a correct way to do this. I don't really care at this point where you put the dots. I would just say don't put more than 2 dots on any one side of the aluminum, okay? These things basically have 4 sides if you think of them like a square, so you can put 2 on each side to total up to 8, okay? But since we only have 3 valence electrons here, I'm just going to put 1 here, 1 here, 1 here. Again, it doesn't really matter to me where you put them, okay? As long as you get 3 dots around your aluminum, we're good. Right. Yeah, you just need to do as many as you need to get the hang of it, okay? All right, so silicon is the second one here. What's the symbol for silicon? Si? How many valence electrons in silicon?
4.
Are we in agreement that that's 4? Okay. So in the group right next to aluminum, okay, group 4A or group 14, depending on what periodic table you're looking at. So that's got 4 valence electrons. So I'm just going to put 1 dot on each side. Again, it doesn't really matter to me if you want to put 2 dots on the top, 2 dots on the bottom. Okay, whatever. Potassium. What's the symbol for potassium? K. Now that one's a little bit tricky. Well, the symbol is a little bit weird on that one, but you guys got it. How many valence electrons with potassium? It's in group 1, so it has 1 valence electron. So just pick a spot and put a dot. Rhyme. Okay, so that makes sense, right? Everybody okay with what you're supposed to do on that chart? Yes, ma'am.
For sulfur, do you need dots on all the sides? 2, 2, 2.
Okay, so for sulfur, you can put 2, 2, and 2, or you can, if you want dots on all the sides, then that's fine too. Just make sure that there are, how many dots are on the sulfur? How many? 6. Just make sure there's 6 dots around the sulfur. Okay? So that's how you do the first chart. Now let me show you the second one, because the second one's a little bit different than that. This one, it says determine the common oxidation number, in parentheses, charge, for each of the following ions. Okay? So now we have to figure out what charge these things are going to have, and then draw their Lewis dot structures. Now, there's a little trick with these. When you draw a Lewis dot structure for an ion, you have to put brackets around it. I don't know why. It's just kind of the way that it's done. All right? So, aluminum ion. Well, first of all, we just draw the symbol like we did before, okay? Now, how many, this is tricky, okay? This is especially tricky for the ones that are cations. How many valence electrons does aluminum have? Typically. It typically has 3, right? Now, what's the charge that aluminum forms? Positive 3. Now, how does it form that positive 3 charge? What does it do in order to form a plus 3 charge? Doesn't share, because remember, we're not talking about covalent. It either gains electrons or it loses them. To become positive, what do you have to do? Gain or lose electrons? You have to lose. How many? 3. Interesting. So that aluminum did have 3 valence electrons. It just lost all 3 of them, right? Okay? So, I'm trying to decide how I want you to show this. I should have decided this ahead of time. Okay, let's think about this. So aluminum has 13 electrons, right? Okay? When it loses 3 electrons, now it has 10, just like neon. Now, how would we draw the Lewis dot structure for neon? How many valence electrons does neon have? Has 8, right? Okay. So let's now put 8 valence electrons around the aluminum. The reason the aluminum lost 3 electrons is so that it could have 8 valence electrons like neon, okay? But then I have to put brackets around this thing. And what charge did you tell me that it has? 3 plus, okay? Basically all of these, I'll give you a little hint right now, they're all going to have 8, right? Because when these things form an ion, they do it so they can have 8 valence electrons. Does that make sense? Now, there's one exception, and it's right here, the hydrogen ion, okay? How many valence electrons does hydrogen have? How many electrons does hydrogen have? 1. It only has 1 electron, right? So when it loses that electron, it doesn't have 8. It has 0, okay? So for hydrogen, you would just write H. Oh, that's weird. You'd write H with no dots, and then you'd put a 1 plus, okay? But everything else on this list, make sure that I'm telling you the truth here, everything else on this list is going to have 8 valence electrons, okay?
Why in the top one did you put helium and you put watch out?
Oh, and the top one? Okay, because helium's in that noble gas column, but how many valence electrons does it actually have? 2, because it only has 2 electrons, right? So helium's the one exception here, because it only has 2 valence electrons, it can't have 8 valence electrons, right? Does that make sense? It only has 2 electrons total, so helium would be the only one in the noble gas column that doesn't have 8. It only has 2. Okay? So when you draw its dot structure, you would just put helium with 2 dots around it. Okay? Now, silicon, now this one's a little tricky. You can kind of choose on this one, okay? Because honestly, it could probably go either way. I think I have a way that I would tend to prefer it, but it doesn't really matter. It's going to have 8 valence electrons, right? Because it's either gaining or losing electrons. How many electrons does it have to lose or gain? 4, okay? So you can kind of pick either one because it's right in the middle, right? I'm going to pick 4 minus just because I know a little bit more chemistry than you guys and I like that better. Okay. Oh, okay. No, there we go. Perfect. Okay. But if you had said 4 plus there, I would have been fine with that, all right? Because you kind of have to choose on that one. Okay, let's do potassium because potassium's a little bit easier. How many valence electrons for potassium? It typically has 1. Okay, once it loses that 1, now how many is it going to have? 8. Is everybody okay with that? That does seem a little weird, doesn't it? If you have 1 valence electron and you lose it, then you're going to have 8. Okay, let me draw something for you here that might help you. So you've got potassium. So let me do something a little easier than potassium because I don't feel like drawing out 4 energy levels. Let's do, we'll just do sodium, okay? So sodium is going to look like this. If I draw the Bohr diagram for sodium, it's going to kind of look like this, all right? So I've got 2 electrons in this first energy level. My alignment's off here, so yeah, this is not working. I need a different color. I feel like I have to do everything in black. Okay, so if I'm drawing sodium, and I'm going to put the valence electrons here. We've got 1 valence electron. We've got 8 on the energy level below that, and we've got 2 in the first energy level. That's just kind of the way that it works, because you can only put 2 electrons in that first energy level, that first row. After that, there's 8, and then after that, you could put another 8 up here, okay? When sodium loses that 1 valence electron, watch what happens, okay? I hate this. I could just draw this on the board for you, and it would be so much easier, but I have to do it this way because of the video. Because there are people who actually are missing today. Okay, let me see if I draw it nice like that, maybe it'll work. Okay, so just pretend that you've got the 8 now. I gotta draw it. 5, 6, 7, 8. Okay. You can do it. All right, there we go. So this one valence electron goes away. Now how many valence electrons do we have? 8. See how that works? Okay? Because you lost the electron in the outer energy level, so that's no longer the outer energy level. So now you've got these 8 electrons that become the valence electrons. Okay? Does that help at all? I was doing sodium just because it's easy to draw, but it's basically the same as potassium, or anything that's losing electrons. Okay? So potassium loses its 1 electron, so now it has 8 valence electrons. Okay? So then we'll draw this with 8 and a 1 plus charge. Okay? I think we're going to maybe need a little bit more time on that on Monday. So don't worry about doing this for homework. I want to give you some time in class to work on this. We can go over it together. And then we'll see how we're doing. We might hold off on this quiz until Tuesday. Or Wednesday, depending on if we're here Monday or not. Okay?